Okay, so let's talk about Dalton's law of partial pressure. So how do you calculate the pressure of a container with a mixture of gases? So in a mixture of gases, what we say is that they don't necessarily have much of an impact on the pressure if they're colliding with each other. Instead, you're going to have a pressure that's given for each individual gas as it exerts on the container itself. So essentially, you can have a mixture of gases, and each one of them is going to have a partial pressure that will contribute to your overall pressure that you measure in the container. So essentially, what it is that your pressure total is the sum of all of your partial pressures. So again, my little atmosphere here, we have helium plus argon gas. Helium has 2 atmospheres. Argon has 4 atmospheres. Your total pressure is 6 atmospheres. Should not be there. Okay, skip that one. So a gaseous mixture made from 6 grams of O2 and 9 grams of CH4 is placed into a 15-liter container. What is the partial pressure of each gas and the total pressure in the vessel? So we need to convert from grams of O2 to moles of O2. And we need to convert from grams of CH4 to moles of CH4. Now, if you're ever going from grams to moles, you need to calculate your molar mass. So our molar mass for oxygen is 15.999. If we're doing O2, we need to multiply that by 2, which should give you 31.998 grams per mole. Here it's a little bit more complicated. So our molar mass is going to be our molar mass of carbon plus 4 of our molar mass for hydrogen. So our carbon is 12.011 while our hydrogen is 1.08008. So we have 12.011 plus 4 times 1.008. So our molar mass is going to equal 16 plus 16.043 grams per mole. Okay, now we set up our conversion. So we start with 6 grams of oxygen. And we want to go from grams, which is going to be 31.998 grams of O2, to moles of O2. And so we get 0.188 moles of O2. Now we're going to solve for pressure. So when we look at PV equals nRT, okay, we're going to divide this by V. So P is going to equal nRT over V. And so our N is going to be 0.188 times 0.08206. And then remember, if we have our 0 degrees C, our T is going to be 273 degrees Kelvin. And we're going to divide this by our volume, which is 15 liters. And so our pressure for our oxygen, rounding to 3 sig figs, is going to be 4.21 atm. And so that's our pressure for our O2. Now we look at our CH4. So we have 9.00 grams of CH4. And we want to go from grams, so 16.043 grams of CH4 to moles of CH4. And so, rounding to 3 sig figs, that's going to give us 0.561 moles of CH4. Again, we're going to use the PV equals nRT. So our number of moles is 0.561 times 0.08206 times 273. The only thing I'm changing here is my moles of my gas, because I have a different value of grams of my gas. And it's a different gas that we're using. But everything else is going to remain the same, because we're going to assume that these guys are kind of working independent of each other. So P for our CH4 is going to be and so our pressure here is going to be 0.837 atm. And so then to get our P total, we add those two numbers together. To get 5.05 atmospheres of pressure. Whew, that was a lot of math. Okay, so hopefully that makes a little bit of sense. Like I said, as long as you know what you have to find the pressures, but if you know once you find the pressure for each individual gas, you will be able to find the overall pressure. So let's talk a little bit about the kinetic molecular theory, and this kind of goes into why we've been talking about gases the way we've been talking about gases. And so the kinetic molecular theory states 5 major things. First is that gases are in continuous random motion. You cannot really predict where a gas is going to go very well because they're constantly in motion and they're constantly going in the way that you think they're not supposed to. We're going to talk about any time you have the combined volume of all the gases is negligible, because remember, there's a lot of space between gas particles. So the overall volume of the container should be significantly higher than what the gas particles volume actually contributes to that container. And so we kind of say right now we assume that it's negligible when it comes to the kinetic molecular theory. Real gases, in all reality, do have a little bit that is contributing to it, but for our purposes, we won't worry about that. So the attractive forces between gas molecules are typically negligible. And so that means that, we have attractive or repulsive forces. And so we're not going to have a lot of collisions with other gases. They're going to kind of move at their own independent, like running and, movement that's of their own making. And then the energy can be transferred between molecules during collisions. However, average kinetic energy doesn't really change with time as long as your temperature remains constant. Obviously, if you change your temperature, you're going to increase your energy for your gas molecules, and so they are going to move faster. And then the average kinetic energy of the molecules is proportional to the absolute temperature. So whatever the temperature is, like we can look at the temperature. If it's low, it's probably slow. If it's the gas particles are moving slow. If it is high, gas particles are moving fast. Okay, so now that we're done talking about gases, let's talk about some liquids. So there are some different properties of liquids that we need to talk about. First is called viscosity. So liquids, even you can be in a liquid state, and if you think of like glycerol or anything along those lines, like it doesn't really want to flow very well. It's kind of slow to come out of your bottle. Um, that's what we call that, like resistance to flow is called viscosity. And what that means is that essentially if something is viscous, it means it doesn't want to flow very well. It's kind of like you try to pour it out of the bottle and it's going to be like you're going to be watching it for a while. So when we talk about viscosity and IMFs, if you have stronger intermolecular forces, especially for liquids, if you have stronger intermolecular forces, meaning essentially when we look at this for our series of hydrocarbons, the longer the chain, the higher the IMF force for the van der Waals molecules, for the London dispersion forces. So higher chain or longer chain equals higher dispersion. Okay, so if you increase the stronger intermolecular forces, as you increase the higher temperature, your viscosity will actually decrease because what you're doing is you're going closer to that transition state between a gas and a molecule, or a gas and a liquid. And so the viscosity, when it look at gases, like we cannot apply this to gases at all because they're constantly moving. And so as you add more energy to your particles, the viscosity is going to drop because it's now going to be more likely to flow. So we have another topic that's called surface tension. And essentially what surface tension is, it's the layer of molecules on a surface of a liquid. And they behave different than those on the interior. And that's because typically when you look at a solid, there's going to be some attractive forces because typically solids are polar or they are ionic compounds a lot of the time. And so what happens is that there is metallic compounds. There is an attractive force that kind of creates a bubble. Now, if you had that on the interior, like they're only interacting with the molecules inside your liquid. But when you're looking at the exterior, that is dealing with cohesion forces between the surface of it and the surface of the solid, and so this becomes more of a the intermolecular forces are stronger, so the attraction is stronger, and so it kind of acts more like an elastic skin. So the resistance for a liquid to resist an increase in its surface area is called surface tension. And so basically, depending on what you're looking at, if you're looking at something that is a liquid that is a nonpolar molecule, like there's going to be much more of a resistance or surface tension if you put that on a polar substance. So the stronger the molecular force is, the higher the surface tension will be. And so so it's kind of the opposite of what we did with viscosity. The stronger the intermolecular force is, the higher the surface tension will be. That's obvious. If you raise a liquid, you'll reduce its surface tension because, again, we're getting to that gaseous state where we run into everything. So when we talk about temperature, remember when you're looking at liquids, the average, and especially even gases, when you raise the temperature, you're adding more energy to your molecules. And so therefore, the molecule's average kinetic energy is going to be higher. So that's why it's easier to stretch that over a surface that you're looking at. So other properties that we can talk about, we talked a little bit about vapor pressure already, but that's the pressure of a liquid as it's transformed into a gas against the container. So when we look at IMFs in this situation, we are going to be looking at seeing that intermolecular forces will decrease as increases as the intermolecular forces decrease because they don't typically want to be part of the liquid, so they're going to resist it a little bit more. And again, your boiling point, if you have stronger intermolecular forces, you're going to have a higher boiling point. Okay, so now let's talk about a little bit about capillary action. And again, this is just going to be a little bit conceptual. We're not going to do any math with it. It's just to let you know why capillary action really happens. So capillary reaction is the ability of a liquid to flow up a narrow tube of a small diameter against the influence of gravity. So you're not really doing much anything else. The liquid will just come up through that capillary. And so you want to have a significantly higher diameter, or the narrower the diameter, because it's kind of like a phenomenon is what happens. The liquid goes up there because it is essentially getting pulled out of the system. And so again, here's some examples of it in action. Plants dry, water from the fruit of their leaves, paper towels absorb a spill on the kitchen floor. Like, those are all capillary actions. You have a bunch of little capillaries that are in those leaves and that are in that paper towel, or even in a cotton towel, that absorb that water or whatever it is that you spilled on your table. So when we look at this, we look at the difference between adhesive and cohesive forces. So cohesive forces, they hold the liquid molecules together. So this is pulling the interior liquid with the adhesive forces. So again, this is kind of like the surface tension acting to hold the surface intact. When you're looking at adhesive forces, you're looking at what the attraction is to the outer container. So cohesive forces is H2O to H2O if we're looking at this. So it'd be H2O to H2O. If we're looking at adhesive forces, that's H2O to container. And so it'll pull liquid up the side of the tube because of those adhesive forces, not because of the cohesive forces. So this idea of adhesive versus cohesive forces will tell you what happens with a meniscus in a beaker or in a graduated cylinder. So essentially what happens is remember, in a meniscus, you have your tube here, okay? You have some liquid, and for the most part this semester when you've done it, you've seen it go, the meniscus go kind of like that, to the best of my ability to draw it. Well, so the reason why that happens, this is specifically for H2O, let's say, is because the adhesive forces of the water molecules to the outside of the container are stronger, and so therefore they kind of lift them up a little bit, so that's why you get that curve. On the other hand, if you put mercury in a thermometer or in anything else, you're going to see something, a different phenomenon happen. So what happens when you put mercury in is you get this type of a situation. And so this means that your cohesive forces within there are stronger than the adhesive forces to the container, and so you get a convex curve. Okay, what the idea here is that when we look at H2O and those liquids, they're only dealing with IMFs, specifically for this one up to hydrogen bonding. Whereas on the other hand, if we're looking at convex, the metallic bonding is going to be stronger. Okay, phase changes. What are the different phase changes, and what is the heat of fusion, heat of vaporization, and heat of sublimation? So when we look at going through phase changes, again, remember our three states of matter were solid, liquid, and gas. And so if you're going from a solid to a liquid, you are melting. If you're going from a liquid to a gas, you are freezing. If you're going from a gas to a solid, this is going to be sublimation. This is deposition, if you're going from a gas to a solid. Okay, and then if you're going from a liquid to a gas, you're going to do evaporation. If you're going from a gas to a solid, or a gas to a liquid, it's going to be condensation. Okay. So as you go through each one of these times, you require some form of energy, right? So we call this energy is needed here. You need energy here. And you need energy here. So when we look at this, we have the heat of fusion. That's going to be the energy required to change a solid to a liquid at its melting point. When we look at the heat of vaporization, we're going to the boiling point, and that's the only difference. So essentially, and heat of sublimation is if we were going directly from a solid to a gas. That's not going to see that very often, but it is an option that you could see. And so this leads us into the idea of heating curves. So essentially what heating curves are, it's just a situation. You're going from temperatures, and this is telling you heat added that you needed to do. So your first temperature is ice. This will have some Q value, so we're going to call this Q of ice. Q is what we're going to use for heat for the moment. This is going to be your Q for, this is going to be from delta H fusion. This is going to have some type of Q for water. And this is your delta H for boiling. Or delta H vape. And then the last one is going to be your water vapor. And that's going from top to bottom. Again, so you remember creating more cohesive forces requires more bond energy. So if you're creating more cohesive forces, you're going to require more energy. Breaking them requires just as much energy. Now, when we're looking at this, you're always going to be given C here, at least for right now. But what you're doing is to calculate for Q, you're going to have your mass and your change in temperature. So if I was looking here, I was going from 25 to 0, my change in temperature would be 25 degrees Celsius. When you're looking at delta fusion, you're not actually seeing a temperature change per se. You're just seeing them start to go from a solid to a liquid or a liquid to a gas. And so you just take your mass times your delta H of fusion, which will be given. And same thing with your delta H of vaporization. That'll be given. Okay, and as you can see, you go from a solid, liquid to a liquid, gas, and then you finally get to your final gas. And so here, we're looking at Q ice, which that's just going to be MC delta T. Here, we have vaporization. So that's going to be, here, that's again, Q ice is going from here to here. I'll erase this there. When we're going from a solid to a liquid, that's going to be delta H fusion, and we're going to multiply that by M. Here, if you're going from a liquid to a liquid close to its boiling point, that's still going to be MC delta T. Difference is that we're looking at it from our solid, and our gas and our liquid are going to be different delta C's. Then when you go from a liquid to a gas, you're going to have M delta T or M delta H vape. And finally, this last one is just going to be MC delta T, and your C is going to be for your gas molecule, whatever it is. Okay. Okay, we will come back to these in the next video. So I'm going to stop here, and we will do these in our next video.